Hello, myself Naveen Kumar Saini. In the course Wireless and Mobile Communication, code KEC 076. Today we are going to discuss about the next very important topic, that is fading. So these are the content which I will cover in this lecture. First is fading, in the basic definition of the fading, then its type, large scale fading and the small scale fading. So first thing is, what is the fading? And we must know about what is fading actually is. It is in the channel. This is the first thing which we have to take care, as a noise in the transmitter or the receiver. So what is the fading? Fading is nothing but, this is the time variation of the received signal power due to the changes in the transmission medium path is known as the fading. So when the transmitter transmits the signal and it is passed through the channel, so because of many obstacles, it may be within the channel or it may be near the receiver. So the signal which is transmitted, it is scattered and it follows the multi path into the system and it reach at the receiver by passing the multiple path. So it depends when it receive at the receiver, so that is added constructively or at the destructively. So this because of this reason the signal strength will be reduced. So this reduction of signal strength or the attenuation into a signal is called the fading. So this occurs because of the fluctuation of the signal due to the multiple obstacles within the channel. So what are the major factors which impact on the fading? That is atmospheric condition. This is the first thing. Just like in the wireless system, if we talk about, then depends if these are just like the rain. If rain is into the environment or the fog or the water drops, so because of that one the signal strength will be reduced. So these are one of the factor which also comprise, as I said, about the rainfall and the lightning. This is also the major factor. Second thing is the geographical position, time, radio frequency and many more. So these are the factors which influence the signal strength or reduce the signal strength which occur due to the fading. So in the diagram it is represented, if this one is the signal which is transmitted by the transmitter and it is received at the receiver. So in this follows the multiple path, as I said. It can follow like this, it will follow and reflected by this will follow and it will reflected by this, and this is the line of sight path which is directly between the transmitter and the receiver. So multiple path of the same signal is representing like this, okay. So but it is combined at this receiver. So if we see closely that this multiple path, just like path number 1, path number 2, path number 3 and so on. So when it is receiving or when it is reach at the receiver, so it is coming with some different angles. So this is follow one angle, second angle, third angle and so on. So this angle of arrival of these signals at different at the receiver side. So then after that it will combine, because many signal which is follow this multiple path, it will reach at different time instants, okay. Suppose this one is reaching at t1, tau 1, this is tau 2 and so on. So time is also one factor because of which when it reach at the receiver, so multiple components will reach at with different time instants or the delays, and it combine at the receiver. So two main things are there. First one is it is reaching at different paths by different delays. Second, angle of arrival at which it will be reaching at the receiver side. So these two are the in mathematical model, these two components we take care when we solve this type of composite problems. So another factors which influence the fading, that is, first one is in the fixed scenario. In the fixed scenario, the fading depends on the atmospheric conditions such as rainfall and the lightning. Second scenario will be in the mobile scenario. What is that? In this case, the fading depends on the obstacles over the path which are varying with respect to the time. Okay, and these obstacles create the complex transmission effects to the transmitted signal. So, as I said, when your receiver is in motion with respect to the transmitter, so in that case the Doppler effect will come into the picture, or the moving objects are there within the channel. So, this also creates the interference at the receiver side when it is combined. So, ISI can occur. Okay. So, because of these reasons, these fading effects will occur at the receiver side. So, broadly we classify the fading type, large scale fading and the small scale fading. So, large scale fading will be considered due to the path loss and the shadowing, and this occurs because of the obstacles, big obstacles like mountains or the buildings within the channel between the transmitter and the receiver. So, path loss will occur and the shadowing effect will occur because of the large buildings or the large obstacles. In the second classification, small scale fading, so which is very tedious to tackle. So, this will be found based on the multipath delay spread and the Doppler spread. So, this small scale fading will based on multipath delay spread and the Doppler spread. So, now this multipath delay spread again classified in the flat fading and the frequency selective fading, and this Doppler spread, this is occur in the influence, that is the fast fading and the slow fading. So, basically small scale fading is comprised in the 4 parts: flat fading, frequency selective fading, fast fading and the slow fading. So, this is completely based on multipath delay spread or the Doppler spread. So, there may be the combinations like flat fading can be with the fast fading and the slow fading, and frequency selective fading will be maybe the fast fading or maybe the slow fading. So, these combinations we will discuss in the upcoming slide. So, first thing is when we talk about the large scale fading. So, here we see in the diagram that transmitter is here, transmitter signal, and it follows the multiple path, or we can say the same copy of the signal is following the multiple path and it is reaching at the receiver, right. So, one path is this one, second is this, third and fourth. So, it combined at the receiver. If there is a delay, sufficient delay between the 2 copies of the signal, in that case the overlapping can occur. It shows here, if one sample copy is this one and second copy is this one. So, in this case the first signal will be completely destroyed. So, ISI effect will come into the picture at the receiver side. So, it shows the fading. So, fading is the effect and result of fading is the ISI at the receiver side. So, this large scale fading occurs because due to the obstacles for the radio propagation over the long distance. Next is small scale fading. This small scale fading, as I said, this is very near for the near to the receiver. So, the fluctuations in the signal strength and phase over the short distance and a small duration of time. So, this is very tough to tackle in the wireless communication system. That is a small scale fading which is near to the receiver surroundings it occurs. Okay. So, now large scale fading, in that, as we said, in the large scale fading when we take it in the logarithmic scale and the linear scale. So, in the logarithmic scale can be defined in terms of the path loss. Okay. So, this path loss can be taken care by this modeling of long normal, and average attenuation is exponentially proportional to the distance. And second effect in the large scale fading is the shadowing. Okay. So, first one is the attenuation and second one is the shadowing. So, the shadowing occurs due to the diffraction by the different large obstacles like buildings, mountains. So, this creates the fading effect. And okay. So, now in that large object is the main option parameter due to which the large scale fading occur. So, this large scale fading is mainly due to 2 effects, as I said, path loss and the shadowing. So this how to mitigate this large scale fading. So this mitigation techniques which we have for the large scale fading, which includes the power control and then antenna placement and the repeaters and the site diversity, right. So based on that, large scale fading can be mitigated, or you can say we can reduce it. So power control, by this power control we use the different antennas, so which we transmit the signal with the different power levels as per the condition of the channel. Okay. So then based on that we have to place the antennas, means if the channel conditions is not good, so in that case how many antennas we can place in at the transmitter side and the receiver side. Then the repeaters and the diversity, site diversity. Diversity means the how many different cells we can accommodate or deploy into the geographical area, so that this fading can be reduced. So in the small scale fading, as Doppler effect is mentioned here, that this is the transmitter side and this is the receiver. So this transmitter can follow the two ways. First one is the LOS. If this mobile phone is, or the subscriber or the receiver in the moving car, in that case if it is the LOS, line of sight, so the signal will receive from the line of sight, and another signal can comes from the different path, as I said before, right. Okay. So it shows the different path which is following by the transmitter, and it is reaching at different angle of arrival. Okay. Some will come at this angle theta1 and some will come this angle theta2. So at different angle of arrivals are there at the receiver side. So Doppler effect will occur when this receiver in the moving, or you can say the receiver, the mobile phone is into the car which is in moving state. So in that case Doppler effect will come into the picture. So these moving objects are also occur, and by which the reflections can occur. So they are a very tedious job to tackle this small scale fading. So as we said before, but the reasons are mentioned here, that random frequency modulation due to the varying Doppler shifts on the different multipath signals. Second, time dispersion echoes, and which is caused by the multipath propagation delays due to the nearby objects. So these are the some of the regions, and one or most movement of the surrounding objects. So which these regions are very much sufficient to understand about the small scale fading. In that when the direct signal or the LOS or the NLOS signals are coming, like if this is a direct signal, which is the LOS, when the transmitter and receiver are at the line of sight. Second signal can come from the reflected or the delayed version of the same signal or the same sample. So in that case some width of the signal will be increased and some will be reduced. Some will increase, some will reduce. So in that way this spreading signals are there. So when we combine these two signals, then the resultant will be some crossovers are there. Into that we can see some crossovers are there. So it means some because of that one this ISI can occur, right. So this ISI can occur and we have to reduce this. So there are the different methods for reducing the ISI into the signal into the at the receiving side, so that we can mitigate the ISI part. So to measure delays, we have some parameters. What are those parameters? So we will say one by one. So in that, first we must know there is some finite delay between the time at which the antenna receives the first copy, which is the one copy and of the signal and on the shortest path, and that which it receives the last copy of the same signal on the longest path, right. So there is a delay. Suppose this one reaching at the tau naught and this one is reaching at the tau n. So in that case total delay will be what? Tau n minus tau naught. So tau naught is for the first copy of the signal and tau n is the last copy of the signal. So total time delay which is observed at the receiver, tau n minus tau naught. So that is also called the maximum delay time spread. So this is the total time interval during which the reflections with the significant energy arrived, right. Second parameter to measure this that is a root mean square delay spread, and it is the standard deviation or root mean square value of the delay of reflections. That is the, if as we are very much aware, when we this one is the variance. So when we take the under root of this one, then we will get the standard deviation. So based on that we can calculate the different delays of the different components. So that in that this weighted proportional to the energy in the reflected wave. So this formula we are very much aware how to calculate that in this way, right. So here two parameters we have discussed about the maximum delay time spread and the root mean square delay spread. So here we see the graphical representation of all these things. This is inter-symbol interference due to the delay spread. In that we see this is the different multiple copies of the same signal. Suppose tau naught, as I mentioned, tau naught is the at the time instant tau naught we are getting the first signal, and at the next time instant, that is tau naught, tau 1, we are getting the same signal but with some delay. Then at the time instant of tau 2 we are getting the same signal with the another time delay, right, and with the different amplitudes. So it is representing here, this is the d t minus tau naught. This is the signal which we are receiving at the tau naught delay. This is representing the signal with the tau 1 delay, and this is representing the same signal of the copy at tau naught delay. So at this time when we are combining all these things at the receiver side, so the resultant signal will be like this one. So all these things when we combine it in this way, when we are combining this signal, this one with this, and this one with this and this, and this one, this and this. So if we see this, that in that case the signal strength will be different. Like see, this one is coming when this is for the tau naught at the time instant t naught. This one is for the t1 and this one is for the t2. So at this different time instants we are getting the different amplitudes of the signal. These are the different amplitudes of the signal. So the composite signal will create the ISI or the inter-symbol interference. So and so on. When we combine all this like this, as I mentioned, so this type of graph will, which we will get it, this type of waveform we will get it. So this creates the ISI. So what are the way in wireless communication system, if we talk about the LTE system or 3G 4G system, so what is the way to reduce the ISI? So in that way, one of the very most important way is to use the ISI. So there are different types of equalizers are there which are used to reject the ISI. These equalizers are always mentioned here. So when we to reduce the ISI, this is one way. Second way is using the orthogonal frequency division multiple access techniques or modulation techniques to provide ISI rejection mechanism using the cyclic prefix. Okay, orthogonal, we are aware that we are using the different orthogonal basis functions onto which the different modulation different modulatory signals are superimposed into that, and we combine that. So for that we use the FFTs. We use the concept of FFT, fast Fourier transform, so that this wide band signal can be converted into the narrow band signal. So this is the method by which the orthogonal frequency division multiple axis can be used to reduce the ISI. Next is, it is possible to remove the interference between the different symbols using the if filter, that is Nyquist zero ISI criterion. So in the digital communication we have already discussed about this, about the what is the Nyquist zero ISI criterion, by which this is nothing but a kind of filter which can be used to reduce the ISI. So next is, it is also possible to manage ISI by controlling the transmission rate in general. Okay, so when the channel condition is not good, so in that case we will transmit the signal with a low data rate. If the channel condition is good, is perfect, in that case we can use any kind of modulation technique, right? As we are aware that how many types of modulation techniques are there, we have many, like BPSK, QPSK, or MQAM, right? So if we have a very bad channel condition, in that case we will use the BPSK kind of modulation techniques. If the channel condition is perfect, then in that case we can use the M shape. M can be 16, so this M can be 4, 16 means 2 to the power n. Okay, so based on that we can use the different modulation techniques. So as if the if this is a 2 key, if suppose M is equal to 16, so in that case this is 2 key power 4. So it means 4 bits can be transmitted at a time, right? So in this way the transmission rate will be increased. So there are some of the definitions. First one is the coherence bandwidth, by which the channel case can be considered, means the channel is flat fading or the frequency selective fading, right? So this coherence bandwidth, we can talk about that for reliable communication without using the adaptive equalization or other anti-multipath techniques. The transmitted data rate may be much smaller than the inverse of the RMS delay spread, which is called the coherence bandwidth. Means in this coherence bandwidth the signal components can be absorbed, all signal component can be absorbed. If signal bandwidth is greater than the coherence bandwidth, so in that case the fading will occur. If the signal bandwidth or the transmission rate is lesser as compared to the coherence bandwidth, so in that case the fading will be flat fading, which can be considerable or which can be handled easily. So the channel transfer function, which remains virtually constant over the coherence bandwidth, it shows that if the channel transfer function is constant, so it means we can aware about the channel condition and we can predict the channel condition, and based on that we can use different modulation techniques to transfer the signals. Then next is the resolvable path. So a wideband signal with symbol duration Ts or a direct DS CDMA signal with a chip time T chip. So when we will discuss broadly about the DS CDMA in the upcoming lectures, then we will discuss about the what is a chip type. So this chip type is nothing but the 1 bit period, 1 pulse period, which can transmit into the channel. So it can resolve the time dispersion of the channel with accuracy about the TS. So for DS CDMA, the number of resolvable path is NP, that is round T delay upon T chip plus 1. So T delay is the total time delay between tau naught to tau n, and T chip is the bit duration of the signal. Okay, 1 bit duration of the signal. So based on that we can find what is the number of resolvable path through which the ISI can be reduced. Okay. So Doppler shift, this is a very much known to all the final year students. This Doppler shift occurs because of the moving receiver with respect to the base station. Okay, so this signal will receive at by the different paths, right? So this is receiving by this LOS, or this can be received by the different paths, right? And in this case this receiver can be changing the phase and the frequency when it is receiving. So we have to calculate the frequency, Doppler frequency, and based on the Doppler frequency, the frequency can increase or decrease when it is receiving at the receiver, right? So next is the small scale fading. This is broadly classified based on the multipath time delay spread, and this small scale fading can be classified based on the Doppler spread. So when we talk about based on the multiple time delay spread, so this can be of flat fading and the frequency selective fading. So what is the condition, or what are the condition for the flat fading case? In that we have the bandwidth of the signal. If this one is less than the bandwidth of the channel, and in that case the flat fading can occur, means all the components of the signal channel can be constant, virtually constant, means this is a coherence bandwidth, right? So that must be bandwidth of the channel must be less than the bandwidth of the channel or the coherence bandwidth. Second way to represent that is the delay spread is lesser than the symbol period, right. Symbol period we can calculate based on the bandwidth of the signal. So symbol period is nothing but this is the inverse of the bandwidth of the signal, and bandwidth of the signal, right. Delay spread also can be calculated based on the inverse of bandwidth of the channel, right. Next is the frequency selective fading. This is the opposite of this case. In the frequency selective fading, the bandwidth of the signal is greater than the bandwidth of the channel, and inverse of this, delay spread is greater than the symbol period. So because of this one, the frequency selective fading occurs, which is very destructive in the case of the wireless communication system. So we have to convert this frequency selective to the flat fading, because in the frequency selective fading, it is very tough to tackle at the receiver side by the channel, and the channel component will change with time. So that is why this frequency selective channel, which is of wide band, you can say these are wide band fading, and this flat fading is the narrow band fading, right. So we have to convert frequency selective to the flat fading. Now come to the small scale fading, that is based on Doppler spread. So again there are two types, which is representing the receiver is moving with respect to the transmitter, right. So because of that one, because of the motion of the receivers or the objects, so Doppler effects occurs, and the in this case the fast fading occurs because of the high Doppler spread. If there is a very high Doppler spread, so in that case the fast fading will occur. And second is the coherence time. This is the coherence time which is very much less than the symbol period. So in this case the ISI can occur when it is receiving at the receiver. Third case is the channel variations. So when the channel variations are very fast as compared to the baseband signal variation. So this is very tedious now. If channel variation is very fast, so what it shows? It shows that we cannot predict the channel. Okay, so we cannot predict the channel. So if we cannot predict the channel, so in that case we don't know what type of signal or what type of modulation technique we can implement for the transmission of the signal. So this is very important to understand what is the channel, how the channel is varying. So this is to be take care. If the channel variation which is very fast as compared to the baseband signal variation, so fast fading will occur. Now next come to the small scale slow fading, sorry, in categorization of the small scale fading. In slow fading, the low Doppler spread is there. Second, the coherence time is greater than the symbol period, and here the channel variations are very smaller than the baseband signal variation. So if we look all the four, what are the best combination out of flat fading, frequency selective, fast fading and the slow fading? If we see the combination with the flat fading and the fast fading, or flat fading with the slow fading, this is the first combination. Second combination can be frequency selective fading with the fast fading, or frequency selecting fading with the slow fading. So which one is the better, right? So if we see closely, because the bandwidth of the signal which is lesser than the bandwidth of the channel, right? So in this case, suppose this is the bandwidth of the signal like this, and this is the bandwidth of the channel. So what it shows, that this signal bandwidth can accommodate into the channel and it can pass easily, right? And similar way, if we have a slow fading, in this case, because the channel variation is very smaller as compared to the signal variation. So what it shows, the channel is not changing very fast. When the channel is not changing very fast, what it shows, that the signal which can be transmitted by the transmitter, and variation will be very less. So attenuation will be very less into the channel. When it receive at the receiver, then the optimal signal will be received at the receiver. So the best combination, if we see as per our understanding, it will be between the flat fading and the slow fading. If we have any other combination like the frequency selective fading with the fast fading, or the frequency selective with the slow fading, so it shows it's not a very good combination. so that we can reduce the ISI. So if the channel is like that, it is very wide channel, so in that case we have to convert into narrow band signal. So if we convert into narrow band, so the low transmitting signals can be transmitted and we combine it at the multiplexers. Okay, so these two are the very good combination of flat fading and the slow fading, so that the signal can be received at the receiver and very less effort is required to retrieve the original signal, right. So here it is representing that about the flat fading which occurs when the amplitude of the received signal changes within the time. So for example, we have the Rayleigh distribution. This is a very general and a very important Rayleigh distribution which we have to go through it. In that we consider all the multipath components. All the multipath components we consider it into the Rayleigh distribution. So it will be helpful to analyze complete channel. Next is which occur when the symbol period of the transmitted signal is much larger than the delay spread of the channel. So in that the bandwidth of the applied signal is narrower. So it may cause a deep fades which increases the transmit power to combat this situation. This is the solution for the combat the flat fading. So it is representing here. So what it shows in the time domain, when this is the signal and it is passing through this channel, then it is spreading signal is there. But in this case the coherence bandwidth, it is representing that Bs is very much less than Bc, that is your coherence bandwidth, and Ts is greater than the delay spread. So symbol period is greater than the delay spread, right. So if this is the case, if symbol period is greater than the delay spread, so in this case the signal which is received at the receiver will be very less distorted. In the frequency selective fading, so which occurs when the multi-path delay spread is greater than the symbol period. So in that the symbol faces time dispersion and channel introduces inter-symbol interference. As I said, this is a very tedious to tackle. So in that the bandwidth of the signal is wider than the channel response, channel impulse response, that is CIR. So it shows that this symbol period is lesser than the delay spread. So this causes the ISI, right, ISI into the system. So these cases we have already discussed, which are the thumb rule to understand about the frequency selective fading. Fast fading, so as we mentioned earlier, this is because of Doppler spread and the rate of change of the channel characteristics, which is larger than the rate of change of the transmitted signals. And in that the channel changes during the symbol period, channel changes because of the receiver motion as we mentioned earlier, and the coherence time of the channel is smaller than the symbol period of the transmitted symbol. So these are thumb rules which we have already mentioned in the classification of the system. So slow fading, which is again due to the Doppler spread, but the conditions of this one is when the bandwidth of the signal is very much greater than the Doppler spread and the symbol period is less than the coherence bandwidth or coherence time. This must be coherence time, sorry. This must be coherence time. So this is the different conditions, and these are the comparison of small scale fading and the large scale fading, which there are different parameters are there, time variation and the cause of that, like time variation, that is small scale is a very rapid, in large scale it is the slow. What is the cause for that? Multipath is the cause for the small scale fading, and the path loss and shadowing is the reasons for the large scale fading. Distance within the few wavelengths, but this is very several wavelengths in the large scale fading. Frequency, which affects individually symbols or bits, and here affect the entire signal. Spatial variations, that is significant variations over the short distance, and here gradual variation over the long distances. When we talk about the typical scale, so very few centimeters to a very few meter, but in the large scale fading it is due to kilometer, when transmitter and receiver are in kilometers. So effects on signal, it can cause deep fades, interference and distortions. It reduces the overall received signal power. Now last, what is the solution for to reduce the small scale fading? That is, we use the different equalizers and diversity techniques. Adaptive modulation techniques are used for the small scale fading. For the large scale fading, we use the power control techniques, antenna placement, repeaters and site diversity. So these all are the complete intuition about the fading, so which is a large scale and a small scale fading, and this will give the feel of how the wireless channel system change when transmitter transmit the signal and receiver receive the signal. So please go through these books. In that, the first one is very important book. This complete fading which we have gone through, that is from this book. So all of you go through this and it will give you the intuition, more intuition about this. Thank you very much.